Welcome to a lecture about the otoliths. Now, there's two organs in the vestibular system that are important, or in the vestibular receptor that are important. One is the otolith, and that basically is a little mattress on top of hair cells that detects linear acceleration. Now we can compare that to the organ of the semicircular canal, which detects rotation by virtue of the fact that it's stuck inside a canal that drives fluid when it moves in rotation. All right, so let's have a look at the otoliths. And I love this organ. Why? Because it detects always gravity, which is linear acceleration, down at 9.8 meters per second. And it also aids in detecting very small perturbations from gravity, or from gravity is going to be more so in that more yaw plane. So let's have a look. Let's delve a little bit deeper. So how I like to draw, I reduce things to the simplest model that I can to think about it. Simple as possible, but not too simple, to quote Einstein. I love this philosophy. It means sometimes I will avoid the use of big words or really specific science when I'm explaining concepts, because basically I'm trying to work with clinical models to help my practice be as efficient and as effective as possible. So I try not to overcomplicate things at the level of engaging clinically. When I'm at home doing the research afterwards or before, yep, I'll go into all the details. When I'm climbing down rabbit holes, yes. But at this level, I want to sort of go top, kind of like more overview level with not too many big words. Even for the clever ones who've been doing this a while, I still find that we don't need to hear a lot of big words when we're trying to get concepts. Okay, so let's have a look at the ventricle, or the otolith. So I draw it like this, like so, and then it's kind of worth sticking the axes there. Well, it will be for the purpose of this explanation. So I just use these. I use X, Y, and Z just because that's what I learnt at school. Now I've done university maths and physics. I was much better at physics than maths, but really I'm not that good. I just like to understand conceptually, and so I've harassed mathematicians and physicists to help me understand this. So I might not get it right all the time, but I think I've got enough to have the conceptual understanding that I need, that I hope I can convey to you. All right, so if you look at these axes, and we'll draw the ventricle like so. That's the striola. We'll draw the saccule, and that's the striola. What we'll see is they occur, this one occurs in, I call it the yaw plane. I call this one the pitch plane. And if it was a plane along here, that would be the roll plane. I just use that terminology because it's head referenced. Now, if you use transverse, coronal, and sagittal, that's more anatomical reference. So I just stick to this nomenclature. And let's look at the head so that we can, when we're working with the vestibular system, its receptor, the vestibular system, and the ear, the inner ear, like the sound apparatus, is actually in a head reference frame. So it picks up head motion. So it's a 3D movement. Now, 3D movement is in the head. So the head can move in 3 dimensions in 6 different degrees of freedom. So it can move 12 different ways, but 6 degrees of freedom. So let's look at what they are. X, or Y and Z, which is lateral to medial, medial to lateral, up and down, and back and forth. Okay, you can also yaw around the y-axis, pitch around the x-axis, and roll around Z. So that's actually 6 degrees of freedom. Okay, so any organ inside the head can move in those 6 degrees of freedom, but what we want to know is which degrees of freedom, or which movements exactly, are able to be picked up by the receptors that are confined to those organs. So we're looking specifically, the otolith, this is how it would be looking. I was going to say that's just how I draw it. It's how I imagine it in the head when I'm thinking about it, just like it is in Herdman. Oh, so we're actually looking at Herdman, vestibular rehab, chapter 1. I think it's page 2 to 18 from memory. So this is page 8, and you can see this diagram here, the saccule utricle. It's called figure 1.9, geometry of the otoliths. Now you'll see the streola here, and the streola is just where the kinocelia change direction, or the kinocelia orientation. So if we're looking at the utricle, you'll see that the actual kinocelias, so the tall ones, the tall hair cells, are lined up towards the streola, like so. I won't get too wild in drawing those in, but you can see that. All right, so in the saccule, it's actually the other way around. So they are lined up away from, and so on and so forth. Okay, so what I try to understand is, well, probably there's one thing that I would like to, what I didn't understand for a long time was I thought that these little mattress otolith organs moved like a mattress with, that could move in all degrees, but they don't. They actually move like only in that direction. They're confined to those specific lines of movement. So, and these do have kinocelia embedded in them, so they do have that tall cell, and when you bend away from the tall cell, you get an increase. When you bend towards, you get a decrease. So this basically opens up potassium channels and then increases your action potential. So this might be arresting, increased, and decreased, like so. So I didn't realize it wasn't kind of all directions, which doesn't make any sense. It only makes sense if you can only pick it up specifically. So let's get back to it. If you look at the utricle, basically if you take this plane and you can move it, so that's your P to A, and in your lateral to medial, medial to lateral, what you can see is you can move in any one of these directions. So if you move this way, you're going to activate this one and turn this one off, vice versa. So that kind of covers us for that XY, or the XZ movement, which is your 2 degrees. Now what you can also see is if you look, if you kind of imagine these guys as little hinges that go like so, and kind of extrapolate that out, it's actually a whole series of transcribed circles. So this one is going to be a little bit more like a roll tilt. Here, a little bit more like a tilt, more so, kind of more so in pitch. So what that means is this organ's going to pick up 1 degree of freedom this way, 1 degree this way, and then also in your roll and also in pitch. Now that's kind of where I'm up to, because I never understood the utricle as being something that picked up more of a pitch plane, because this one's aligned in the pitch plane, right? But when I look at this one and I think, okay, let's draw those little circles out. If anything, that's a roll plane, and that one is yaw. So I'm still trying to get my head around that one, but that's, when I look at it first principles, that is what I see. Now you say 4 degrees of freedom. Wow, that's a lot, because if you look at this guy here, it can only pick up the 1 degree of freedom that allows fluid to move through, or actually this is hermetically sealed, so it hits and pushes, that allows fluid to put pressure through in that direction. So your semicircular canal, it is 1 degree of freedom. This one's 4 degrees, okay? Now the difference between these two is this guy, you can take it to the bank, that if you're twisting in that direction, if that's bending, it's because of twisting. This guy, you can't take it to the bank. You know that if you move this way, so if you move, like, we'll pick an easy one. Say you've got this one and just say it was exactly in that x-axis plane, we pull it out. Oh, here's a convenient one. If you move it this way, for instance, you're going to get the mattress. It's going to stay. And you're going to get a change in firing, or an increase. But if you also, okay, if you move that way, this one goes, yeah. So if you move to the right, you're going to get this. But if you tilt to the, move to the left, because that's looking towards us. If you tilt, so move to the left, this is going to stay behind by inertia, changing this angle here. But if you tilt to the right, you're also going to get exactly the same angle. So what this means is a translation and a tilt gives you the same theta. So even though you can move in these different directions, you can tilt or you can translate, the signal inside the nerve is going to be related to the same theta. And this is what Einstein describes as the tilt translation ambiguity. So I'll reference Einstein a lot because he was such a brilliant thinker and he's littered throughout neuroscience, and he's also a polymath. And I think we can learn so much from looking at the way that other disciplines think, which is why I'm extremely interdisciplinary in my thinking and reasoning and networking, because it just means that you learn more stuff more quickly across more domains and you can solve problems more fast. So the next thing we'll talk about, and I learned I have to credit David Truster for teaching me this. Last time he was out for the AAFN and also for our lecture series, which was over a year ago now. He really helped me understand this. So basically, if you don't know if it's a tilt or a translation, you need something to tell you. Turns out the answer is in these canals. So we'll talk about that next lecture.